basically exhausted, hopefully, and hopefully not that you're exhausted, but we have talked a lot about semi-crystalline polymers, but we haven't really discussed yet about non-crystalline or amorphous polymers. So we're going to get into that discussion today, and specifically into some concepts of TG and other critical parameters for these polymers, because obviously there's some very important polymers that are completely non-crystalline amorphous, polystyrene being one of them, and many others. So let's get into non-crystalline polymers, our glass transition. So these amorphous polymers will not have a TM, they will have a TG, and we know that semi-crystalline polymers also have a TG in those kind of disordered or amorphous regions between the lamella structures. So the key thing that distinguishes between a non-crystalline and amorphous or a semi-crystalline polymer and amorphous polymer is the lack of long-range translational and orientational order of your polymers or your crystals. Actually, there's no crystals or very few crystals. So let's do a quick review of short-range and long-range order. So all materials, non-crystalline, liquids, gases, will have some degree of short-range order, but they will not. Non-crystalline materials will not have long-range orientational order or long-range translational order. I just simplify it with LRO. So what does this mean? In a metal, we know that we have some type of unit cell that propagates. We could translate this unit cell. What unit cell is this? BCC. We could translate this into infinity. If we project it on a 2D plane, what it means is we know where each atom should be basically all the way into infinity. So we know exactly the distance between these atoms, and we could estimate where they are at all times. But with a polymer, we know that polymers are kind of dynamic. They're not static. And these chains kind of fluctuate and move, and that's why we have to kind of take these r² to the 1/2 values to estimate, size. So we're not going to know where each atom, each monomer, essentially is at any given kind of time. But we will understand, or we will be able to kind of deduce some characteristic distances. So there is short-range order because our polymers are connected. The monomers are connected somehow. So if I know one monomer, I know that there's going to be a monomer here at a certain, at least some certain length, some radius kind of away. So short-range order, again, is due to kind of our local chemistry, our connectivity, excluded volume, rotations, et cetera, et cetera, et cetera. But our long-range order, that comes from, okay, these kind of folded lamellar structures. Okay, this monomer is here, but I know that, again, there's some kind of characteristic spacing, so that's going to give me some kind of long-range orientational order. But for amorphous polymers, you can see that that's not really the case. So there's no well-defined unit cell. There's no highly specific or strong, kind of intermolecular bonding. So that is not present for these amorphous non-crystalline polymers. So amorphous at all temperatures. Semi-crystalline polymers will be amorphous and crystalline, again, at some temperatures. So one of the ways that we could kind of deduce whether a material has short-range or long-range order, or the extent of that order, is by calculating or estimating a pair or radial distribution function. You'll hear both terms used. So a PDF/RDF. In this course, I'll try to be consistent and use PDF, but RDF, you'll see that kind of occur. So what is a pair or radial distribution function? Hopefully you remember this from materials science, ENGR 45. You can look at I believe it's chapter 2 in that OER textbook, but we're going to kind of go over it today. So we can basically estimate, get a quantitative measure of the amount of short-range, long-range order in both semi-crystalline amorphous polymers using pair distribution function G of R. So this is a really complicated-looking equation, but I think it's best deduced, or kind of the way that this equation works is really given best by this kind of this schematic here. So to calculate your pair distribution function, all you do is you pick a reference atom. I'm going to give this a color. I'm going to make this a specific color. I'm going to do purple. So you pick one reference atom. And what you do is, again, this is in 2D, but you can imagine doing this in 3D. You start to draw basically circles around this atom. Basically spheres. You create like kind of these cylindrical or these spherical shells around this atom. And you start to increase that distance. And then that distance from this reference point to whatever this radius is, that is your R. So, and then what you do is you count. Okay, this is my reference point. Do I hit any other atoms? So you see initially, like, okay, I'm not hitting any other basically blue circles. So nothing, nothing, nothing. But once I start to hit like this critical or this kind of distance, now I'm hitting 1, 2, 3, 4, 5 atoms. So basically you're counting in these different sized spherical shells, as you can see here. So you're basically changing, you single atom as a reference, calculate the number of atoms, you just count the number of atoms in some spherical shell with this volume, where there's D of R is the thickness of the shell, R is the radius of the shell. That's it. So you're just basically counting the number of atoms, you're dividing out basically by you're normalizing here by basically the dense size of the shell. You're normalizing by the average density, making it a dimensionless quantity. So G of R, again, relative probability of finding it's basically, this is the key idea. The PDF, your radial distribution function, your pair distribution function, your G of R, is the relative probability of finding an atom at any given distance R. So the total integral is not, so just know that. So you could see, and let's look at it here. You get a spike because, again, you're just in this function here. It's the number of atoms that shell is intersecting. So let's go back to our presentation. So you see a spike here. And then again, as you increase, okay, I'm not hitting anything, I'm hitting a few atoms. But then once I hit another one, okay, now I'm hitting another. So you get another spike. So you can kind of think about this as your kind of characteristic distances. So there's some long-range order, but again, as you get further and further out for polymers, you see the number of spikes just kind of dies off and you flatline. When you flatline, basically you reach this kind of value of almost 1, where everything is the same. There's no local order. You kind of hit like your average density of particles. This makes more sense when you look at it in the context of, let's think of a metal. So I'm just doing a 2D. Let's look at a metal. So in a metal, if this is my reference atom, look at, I'm not getting anything until I hit a radius that is equal to my nearest neighbor distance. So for a metal, I'm going to hit my G of R is going to be nothing, nothing, nothing. I'm going to get a spike. And I'm going to get a spike at my nearest neighbor distance. And then the next time I intersect atoms, it's going to be, so these are my nearest neighbors. These are my next nearest neighbors. So once I draw a larger circle, that's going to be my next nearest neighbor distance. And I'm getting another spike. And again, the size, actually, basically if you take the integral of this peak, then you could find the number of atoms that you intersect. But again, that's a little bit further on. So once you integrate that peak, you could take my Engineering 45 class. Integrating that peak will give you the actual number of nearest neighbors. But that's essentially the function. So for metals, again, you're only going to get basically these delta functions because, again, everywhere is locally ordered. But for a polymer, you're going to get these kind of peaks, some peaks, and basically the number and kind of the width of this peak. The wider these peaks, again, it's kind of telling you something about like the less, there's less long-range orientational order because there's not these kind of sharp delta functions. And also the number of peaks, if I have a lot of peaks, it's still saying I have a considerable amount of long-range order before I flatline. A glass or a gas, as we might see hopefully in the next image here, a gas is just going to look like this. It's just a flat line. So this is one polymer here. But if I have a polymer that has a PDF like this, and then maybe that, obviously this has much less long-range orientational order than here. Why? Because there's more peaks that extend at a larger distance, kind of R. So I kind of know these kind of basically more characteristic distances at larger lengths. But if I had a polymer like this, lots of peaks and sharp, I can't really draw it super sharp here. And it just keeps extending. That's a really, really, really semi-crystalline polymer. There's lots of these kind of peaks. And again, the magnitude here just tells you the number of atoms that it hits. That is a key distinction or a key tool to get a quantitative measure of long-range and short-range order in your kind of polymer. So again, you can kind of find these characteristic distances that are occurring. So that is PDF functions in a nutshell. There's lots of fun examples that you could be given to kind of deduce those, long-range and short-range order. And hopefully, again, this is a little bit of a review from ENGR 45 and material science course. And again, for metals, just like we kind of talked about, first nearest neighbor distance, second nearest neighbor distance, you can integrate that to get, you can integrate any kind of peak that you see to get basically what is the number of nearest neighbors. Number nearest neighbors. So, and that holds for, even for a polymer as well. So you could get the number of nearest neighbors if you just integrate this peak. Yeah. Next time, we're going to get into a much longer discussion of TG, one of the most important parameters, I think, for the distinguished polymers and make them unique from every other material. So the TG, glass transition temperature. So more on that next time, and hopefully some fun demos are going to be coming your way soon. So I'll see you all in the next video. Bye. Have a good one.